read the R permutation of a multiset, that means the ordered arrangements when the set contains the elements with repetition, and that repetition we have considered finite repetition, that means the each element appears finite number of times, or it can be infinite number of times. Now, the way we have defined permutation and combination, if we remember that it is the arrangement, but permutation when it is the ordered arrangement, combination when it is unordered arrangement. So, the similar way I can define the combination of multisets. That means that we can count the arrangements or the counting problems, we can apply that where the unordered arrangement is considered from a set or set having elements with infinite repetition. So, we will read the combinations of multiset. Similar way we can define the combinations, only the difference is unordered arrangement. So, if S is a multiset, then an R combination of the set S is an unordered arrangement of S. And similar way, the way we have defined combinations of sets, I can tell. So, the are combinations of multiset S is nothing but the sub multisets of S, is sub multiset, since it is unordered. So, I can tell this is a subset. So, sub multiset S having R elements, because I am considering R combination. Now, if S has an n object, then there is only one n combination of S. Then only one n combination, and normally we call that is the combination of set, n combination of set S. If S has objects of k different types, then there are k number of one combination of S. These are similar to that normal set. So, if we illustrate with an example, say I consider a multiset S, say if S I take that with finite repetition, say I have A elements with 2 repetition, B with 1 repetition and C with 3 repetition. Then since it is unordered, so I can write some 3 combinations. The sum of the 3 combinations of S is simply 3. So, I can write 2A, 1B, I can write 2A, 1C, I can write 1B, 2C, or it can be 1A, 1B, 1C. It can be, I can write here 1A, 1B, 1C and so on, we can write. Now, we see how we can give the general statement of computing the R combination. So, I give a theorem . The statement I write that let S be a multiset with objects of k types each with an infinite repetition. Then the R combination of the set S we can write as R plus k minus 1 CR, and which is same as that of R plus k minus 1 C k minus 1. And here it is infinite repetition. So, S is of type k type. So, infinite A1, infinite repetition of A2, infinite repetition of A3 and so on, infinite repetition of AK. So, now with this theorem statement we read some problems and how we can actually compute the combinations. We first take a multiset, one example we take as it is the like the theorem statement. Let S be the multiset say I have A with 10 repetitions, B with 10 repetitions, C with 10 repetitions and D. So, there are 4 different types ABCD with objects of 4 types of 4 different types. Then the question is, what is the number of different, or I can write 10 combinations of S which have the property that each of the 4 types of objects occur at least once. So, just like the theorem statement, here S is the multiset having 4 different types of objects ABCD, and each type of objects appear with finite repetition and 10 repetition. 10 is the 10 repetition number. Now, what is the number of 10 combinations of S which have the property that each of the 4 type of objects occur at least once. Now, here if we consider the solution, if we think say if A appears x1 times, B of x2 times, C x3 times and D x4 times. That means x1, x2, x3, x4 are my repetition number. Or other way I can tell that number of A's, number of A's equal to x1, number of B's equal to x2, and like C's, number of C's x3, number of D's x4. So, I can write that the answer is, is same as that of the the number of integral solutions of x1 plus x 2 plus x 3 plus x 4 equal to 10. Since each object appears at least once and it is a 10 combination, so the total objects or total object count should be 10. So, I can tell this is the 10 combinations of this thing. So, I can write that I introduce a variable y1, y2, y3, y4. So, introduce new variables say y1, y2, y3, y4 such that this becomes y1 equal to x1 minus 1, y2 equal to x2 minus 1, y3 equal to x3 minus 1 and y4 equal to x4 minus 1. So, my equation 1 becomes, so the equation 1 becomes y1 plus y2 plus y3 plus y4 equal to 10 minus 4 equal to 6. So, that why we have done, so that these y's become here the y's become non-negative, y's become non-negative. I have to find out the number of non-negative integral solution of this new equation. I can write this new equation as the 2. So, if I continue, I have to find out the number of non-negative integral solution of equation 2. That is y1 plus y2 plus y3 plus y4 equal to 6. So, now if we apply the theorem of the R combinations of multiset S, then I will get that number of non-negative solutions, this becomes I have n is 6, okay, I write, okay. If we see the statement that R plus k minus 1 CR, and this was the R combination of S and k different types of objects. So, we identify here R, that means here R equal to 6 and 4 different types. So, k equal to 4. So, I can write R plus k minus 1. So, 6 plus 4 minus 1 C R, sorry 6, R is 6. So, this becomes 9 C 6 equal to 9 into 8 7 into 6 factorial, because this is 9 factorial divided by 6 factorial into 3 factorial. So, this equal to 6 factorial into 3 factorial, this is equal to 9 into 8 into 7 divided by 6. Is equal to 3 into 4, 7 is 84. So, I will get the total 84 solutions. Now, one important application area of this particular problem, that or these R combinations of set with infinite repetition, is the number of integral solution. How to find the number of integral solution? If we see the previous example, see the examples we have actually converted into that form, that initially it was only that combination, it was given the statement, but we have converted the problem statement so that it becomes that how to find out the number of integral solutions of this equation. So, now if we see this type of examples, that I give a different problem, that say another example if we see, and we give a different solution procedure. Okay. The statement is determine the number of 10 combinations of the multiset M equal to 3, A with repetition 3, B with repetition 4 and C with repetition 5. Now, here the problem is this, and we will apply the inclusion-exclusion principle. So, different solution technique we will be using here. We will apply inclusion-exclusion principle. So, first we consider that we identify the property. So, let P1 be the property that a 10 combination of, say I am making this thing as a M star, one multiset, and M star I am giving that as if M star is that again 3 different types having infinite repetition. So, infinite B and infinite C, we are making this thing. and property that 10 combination of M star has more than 3 A's. See, the original problem, it was that there are 3 A, that means A with finite repetition 3. Now, the property I am taking that P1, the property that a 10 combination of M star has more than 3 S, because that is why we have changed the size of the multiset, and that we take as if this is M star which is infinite set. Otherwise, we cannot consider that element or the A have the more number of A will appear where the more than the repetition number. So, here the repetition number is 3. So, we consider that P1 is that property. Similarly, that P2 is the property that a 10 combination of M star has more than that M star has more than 4 B's, and P3 is the property that 10 combination of M star has more than 5 C's. More than 5 C's. So, these are my that property. So, if we remember that inclusion exclusion principle, that actually the way we have defined that, now let A1 be the of this combination, that means AI. If I continue, let as usual we consider that AI consists of this 10 combination. That means A1 is the A1 concerned with A's, A2 is that of with B's, and A3 is that of with C's. So, if we remember the inclusion exclusion principle, then I can write that the size of the set that it will give, let us the number of, I can write the number of 10 combinations M star that have none of the properties of P1, P2, P3 is equivalent to get the number of 10 combinations of M. Why? If we see the way we have taken that M was that A with 3 repetitions, B with 4 repetitions, C with 5 repetition. Then I have converted M star with infinite repetition, and we have considered P1 as if A appears more than that, has more than 3 A's. A appears more than 3, B appears more than 4, C appears more than 5. So, this is actually complement. So, that is why then if I now apply, so using, if I remember that using inclusion exclusion principle, because that tells that a complement, the cardinality of a complement is the cardinality of set S minus cardinality of A. So, inclusion exclusion principle, I can write the, here it is 3. So, cardinality of A1 complement intersection A2 complement intersection A3 complement, these will be the set S minus sigma AI. So, here it is only 3, that means A1 plus A2 plus A3 minus the 2 combinations plus 2 combinations, then A1 intersection A2 plus A1 intersection A3 plus A1 A2 intersection A3. Then I have another, that all 3 together I have to take, that A1 intersection A2 intersection A3. This is the our inclusion exclusion principle. Now, we have to compute all the values. So, now we use that the R combination of how to compute that R combination of set S. So, S is, I can write that 10, because 10 combination 3 type. So, 10 plus 3 minus 1 C10, which is 12 C10 equal to 12 factorial divided by 10 factorial into 2 factorial is 12 into 11 into 10 factorial and divided by 2 into 10 factorial equal to 66. Now, I have to calculate the other values. Now, how to compute that A1? See, I can write that because there are 10 combinations and A1 we have taken the property that A appears more than 3. So, if A appears more than 3, since I have 10 numbers where that more than 3 means at least 4. So, I have 10, and for when I am considering the property of A1, because that A appears more than 3. Okay. So, this will be 4. So, this becomes 6. So, I am taking that this is 6 plus 3 minus 1 C6 and this becomes 8 C6 and this equal to into this is 8 factorial by 6 factorial into 2 factorial. So, 8 into 6 factorial divided by 6 factorial into 2. So, this becomes 28. So, similar way I can compute A2, which will be A2 will be 5 plus, because B appears more than 4, that means 5. So, it is 5 plus 3 minus 1 C5, and this value becomes 7 C5, this becomes 7 into 6 into 5 factorial divided by 5 factorial into 2 factorial, and this becomes 21. Then A3 is 4 plus 3 minus 1, because more than 5 means 6. So, C appears. So, this becomes 6 C4 equal to 6 into 5 into 4 factorial divided by 4 factorial into 2 factorial, and this becomes 15. Now, the two combinations I can get A1, A2 if I take together. So, this becomes 10 minus 4 plus 5, because for A it is 4, for B it is 5. So, this becomes 1. So, I have 1 plus 3 minus 1 C3 is 3 C1 equal to 3. Now, for A2, A3 this becomes 0. For A2, A3 this becomes 0. Why? Because here this becomes 5 plus 6, 11, and 11 is greater than 10. So, it is not possible, this type of combination. Now, for A1, A3, so A1, A3 this becomes 10 minus 4 plus 6. So, here this 11 is coming from 5 plus 6, B and C. Okay. So, this becomes equal to 0. So, A1, A2, A3 is 0 plus 3 minus 1 C0, and this is equal to 2 C0, 2 C0 is 1. So, I got this value 21, this is 15, this is 3, 1, this is 0. Another value I have to compute A1, A2, A3. So, this is my A1, A2, A3, and similarly this becomes 0, because here this is 10 minus 4 plus 5 plus 6. So, this is greater than 4 plus 5 plus 6. So, 15, which is greater than 10. So, this type of combinations is not possible. So, this becomes 0. So, now if I put that values, all those values with inclusion exclusion principle A1, A2, A3, then I got S, that is 66 minus A1 is 28, A2, for A2 this is 21, this is 15, then for 2 combination we got 3 plus 1 plus 0, then 3 combination it is 0 only. So, this becomes 66 minus 64 minus 4 plus 4, sorry, this term will be plus 4. So, this becomes 6. So, see, the when we are considering that combination with repetition. So, this is one example of combination with repetition. I can apply the inclusion-exclusion principle. So, I can write this is an example of combinations with repetition. This is an example of combination with repetition where we use inclusion-exclusion principle, and we can get this solution directly by applying this. So, directly we can, the earlier example, directly we have applied the theorem of computing the R combinations of a multiset S, and that S has elements with finite or infinite repetition we have considered. And one example we have seen that how to find the integral solution of an equation, and here another example with combination with repetition we have seen that we can use that inclusion-exclusion principle that we have read earlier. In this way we can handle the permutation and combinations.